Let's say we're trying to prove a statement P of n, where it's just some statement, and inside that statement, for a variable, it uses n. And it says n is within the set of all positive integers. So let's say we're trying to prove this statement, this P of n. How do we do that by mathematical induction? Well, by mathematical induction, the logic behind it is that first, what we need to do is we need to see what happens at the base case, at n equals 1, or aka the simplest case. We do this first because we need this to be true in order for the whole theorem to be true in general, because for this proof to be true, right, for this statement to be true, it must be true for all n that are positive integers. So if this base case isn't true, then we can just throw out the statement altogether, right? If this n equals 1 is not true, then we can just throw out the statement as just being untrue, as being false. We can prove it false. But if this is true, then we can move on with our proof, because we've seen that with the simplest case possible, that this is true. So we need to prove that for any arbitrary positive integer that we pick, that it can be true as well. So how would we prove that with any other positive integer that this statement would be true? Well, one intuition that you might come up with is that we can just try every value of n, plug it into this, and we'll just test out if it's true, right? Why don't we do just like n equals 2, n equals 3, n equals 4, and we just do all the positive integers and test them in this proof and see if they're true or not. Then we'll get to know which values are true, and if any of them are false, we'll just say this whole theorem is false. So pretty simple, right? But the problem in that assumption lies that in this set of all positive integers, it's infinite, right? This is an infinite set with infinite many values in the set. So to prove that one of these values is not false for this theorem, we would have to go through every single one, and we would have to go through an infinite amount of values, which is obviously not possible. So this method just does not work because of the fact that we cannot prove an infinite number of values. It's just not possible with current computation, right? With just any computation, actually. It's impossible to test an infinite amount of values if they're true or not. So that method's out the window. So mathematical induction, what it says that we can prove this theorem with is that, so first, let's just assume that n equals k. So we substitute each n with k. No, wait, not n equals k. We'll substitute each value of n with k, where k is in the set of positive integers, but it does not equal n, right? K can be anything, but it doesn't equal n. So we assume when we do p sub k, it's this statement with k as the variable, with k in the set of all positive integers. And the important realization is that we assume this value to be true. We assume p of k to be true. Now you might think, how can we do this? Like, isn't that what we're trying to get at in the first place? How can we just assume that it is true? But our further logic will come to resolve this fact. So next what we do is we try to substitute k. We substitute that in for k plus 1. So we substitute k plus 1 into this, and we see if k plus 1 is true. If k plus 1 is true, when we substitute into p sub k, then we know that as we go from any number n and then we go to n plus 1, this will always be true, right? Because we proved it for arbitrary values of k, right? We proved that from one number to the next, if you input those two into the theorem, then they'll prove correct, right? So from this logic that you prove in the induction hypothesis, you can then go on to prove that your original statement was true. Because we proved the base case, right? And from that, to get to the base case, to any number of n that is just 1 plus n, we can just add a 1 to it, and we will always know that to be true, because we proved it right here. We plugged it back into that equation, and then we proved it to be true, because we assumed the previous one to be true. Because we know that n equals 1 is true, we don't have to assume that. And so whenever we add 1 to this n, we will know for certain that that value that comes as a result is true, because we proved it right here as k, right? Right here, we don't need to assume that n equals 1 equals true like we did right here when we assumed k was true, because we proved that n equals 1 is true because we just plugged it into the equation, right? So as we add an infinite amount of n's, if we do 1 plus 1 plus 1 plus 1, for any value of n, we know for certain that it's true because we proved that any value plus 1, the next value will be true if the previous value is true. So because we proved that n equals 1 equals true, is true, then any other subsequent values will have to be true, right? This is the main logic behind the induction hypothesis. And what you'll find is that actually proving this portion, that k plus 1 is true when k is true, is the hardest part of any induction proof, because you're trying to plug this back in, and it's just a lot of like complex algebra that you have to deal with. But if you can prove this is true, this makes the statement true, then you can therefore prove the theorem for all cases of an integer that is positive is true.